This is the 13th video in my series on three-phase power transformers. In this video, I'll be looking at the per-phase equivalent of a delta Y connected transformer. You can find out more on this subject in my course entitled Electrical Three-Phase Power Transformer Fundamentals. You can access this and my other courses on my Stan Store at this web address. I now want to develop a per-phase equivalent circuit for this type of connection. So I'm going to return to my voltage phasors here momentarily, and I'm going to shift everything to the upper left-hand corner so I can make some room for my equations, and we'll see where that takes us. Looking at the secondary side of the transformer to start with, we can see from the phase relationship the relationship between the phase-to-phase and phase-to-neutral voltages are given by these equations. And the per-phase turns ratio is given by the line-to-line voltage all over the line-to-neutral voltage. Now, in order to look at the phase relationship of the primary, of course, there is no neutral, so we have to come up with a hypothetical neutral, but we can do that because it's a balanced equation. And the procedure for a per-phase analysis, the step one procedure, is to convert all delta loads and sources to their Y equivalents. So we can do that, as I said, by having a hypothetical neutral, and we can come up with the equation that the line to neutral voltage on the primary is equal to the line to line voltage minus root 3 all over root 3. I'm going to take the two equations that we have just developed here and do some mathematical manipulations with them. I'm going to look at these two equations, and I'm going to divide the line to neutral primary voltage by the line to neutral secondary voltage. And then whatever I do with the left-hand side of those equations, I have to do with the right-hand side. So that equates to the line-to-line voltage minus 30 degrees over root 3 all over the line-to-line voltage divided by the turns ratio. And I can make that equation simpler by getting rid of two of the fraction signs, which is just again a mathematical manipulation, which says that the line to neutral primary voltage over the line to neutral secondary voltage is equal to the turns ratio times the line-to-line voltage at minus 30 degrees all over root 3 line-to-line primary voltage. I am going to make the equation even simpler by canceling out the common term in both the numerator and denominator, namely the line-to-line primary voltage, and I'm going to establish the A primed ratio, which is the turns ratio all over root 3. So our equation now becomes the line to neutral primary voltage over the line to neutral secondary voltage is equal to A primed at minus 30 degrees. Now, there is no primary neutral, so I'd like to reestablish this equation using line-to-line voltages, and we've got the conversion there of line-to-line or line-to-neutral voltages by establishing our phase relationships earlier on. And we can now say that, and we can replace the line to neutral values of this equation by their equivalent line to line values. And then I'll simplify the equation as I've already done in the past by getting rid of the fraction signs and the common terms. And so we're left with the voltage primary line to line all over the secondary voltage line to line is equal to the ratio of the line to neutral voltage primary over the line to neutral voltage secondary, which is equal to A primed at minus 30 degrees. This last equation is actually made up of two equations, which can be rewritten with the primary voltages on the left-hand side of the two equations and the secondary voltages on everything else on the right-hand side of the equation, which will help us establish our per phase equivalent circuit a little bit easier, because in a per phase equivalent circuit we're dealing with line to neutral values, and this is a balanced system, so we can bring up the per phase equivalent circuit. And the per phase equivalent circuit would look like this. And we have two operators that we have to be concerned about, and one is the turns ratio for the per phase transformer. We have to establish what we do to the secondary voltage to come up with a primary voltage. In other words, if I'm given the secondary voltage, I have to multiply by the turns ratio A primed in order to get the primary voltage, and that's what's indicated with the yellow arrow there. Now remember, the A primed is a ratio of the regular turns ratio of the individual transformer windings divided by root 3. And the second operator that we have to be concerned about is the phase shift that happens with the voltage going through the transformer. And if we take the secondary voltage and move it and want to know what the primary voltage is, not only do we have to be concerned about the turns ratio, we have to be concerned about the 30-degree phase shift. In other words, we have to subtract 30 degrees from the secondary voltage in order to get the primary voltage, and that's indicated there with the burgundy or purple arrow that you see on the diagram. Now we know, and we've already talked about this before, that if the turns ratio of the transformer is one thing involving the voltage, it's the inverse if we're looking at the currents. So in this case, the current would the primary current, line current, is given by 1 over A primed times the secondary line current minus 30 degrees. So we have to, in going from the secondary side to the primary side, in other words, we have the secondary current and we want to know what the primary current is, we have to divide by the turns ratio A primed. However, the phase shift remains unchanged. It's the same as the voltage. The primary voltage will lag the secondary voltage by 30 degrees, so we have to use that operator to come up with the primary voltage the same way as we do with the voltage. This video is part of my Electrical Technical Information series. In this series, I'll be covering essential topics to help you understand electrical systems. Be sure and stay tuned, as I will also from time to time be reviewing electrical products that, in my opinion, are worthy of paying attention to. Some of those products include 𝐃𝐈𝐒𝐂𝐋𝐀 big and small standby generators. This is the best time to try out any of 𝐃𝐈𝐒𝐂𝐋�'s products because they are having a huge sale starting April 4th and lasting until April 21st. Here are just a few of their products, starting with the 𝐃𝐈𝐒𝐂 Delta Pro and Delta Pro Ultra and the Delta 2 Max, including the River line of smaller standby generators, the Delta 2, the Wave 2, the Glacier, and the River 2 Pro. The River Pro, the River 2 Max, and the River 2. And a range of portable solar panels, including a 400-watt portable solar panel and a 200 watt bifacial, and the Glacier. And finally, a unique product, the Wave 2, which is a portable air conditioner / heater that fits anywhere. To obtain more information on this subject, simply fill out the information requested when you go to this website. Before I end this video, I want to repeat the connection to obtain my free copy of the Ultimate Guide to Residential Standby Generators and receive access to the major April sales on many of the EcoFlow products. Also, here's the connections to obtain a free copy of my 50-page electrical power crib sheets. And finally, here's the link to all of my electrical courses, which are located in my Stan store.